In the grand story of science, some names shine brighter than others. They are like giant stars, lighting the way for everyone who comes after. Two of these stars burn with a special brilliance. Isaac Newton and Albert Einstein. They are the heavyweights, the champions of our quest to understand the universe. For centuries, people have debated a fascinating question. Who was the greater genius? It's a cosmic showdown between two of the most incredible minds humanity has ever produced. Each man fundamentally changed how we see reality itself. They gave us new eyes to look at the cosmos and our place within it. Isaac Newton was born in England in 1643. He arrived in a world filled with mystery. People saw things fall to the ground, but they didn't really know why. They saw the planets moving in the sky, but the rules of their dance were a puzzle. Newton took on these mysteries. He created a set of laws that seemed to explain everything, from an apple falling from a tree to the silent waltz of the moon around the earth. He gave us a mechanical universe, a great clockwork machine that operated on predictable, understandable rules. For over 200 years, his ideas were the bedrock of physics, the ultimate truth. Then along came Albert Einstein, born in Germany in 1879. He entered a world that felt very sure of itself, a world that thought it had physics all figured out thanks to Newton. But Einstein had a restless, curious mind. He wasn't satisfied with the old answers. He saw things that didn't quite fit into Newton's perfect clockwork universe. He dared to ask new questions, questions that would shake the foundations of science. He imagined what it would be like to ride on a beam of light. This simple thought experiment would lead him to a revolution that redefined our understanding of space, time, and gravity itself. So we have these two towering figures, Newton, the man who built the entire cathedral of classical physics, and Einstein, the man who came along and showed us that the cathedral, as beautiful as it was, needed some major renovations. It wasn't about tearing it down, it was about building upon it, making it grander and more accurate. The story of their ideas is a journey through the heart of science. It's a tale of how one great mind can stand on the shoulders of another, see a little bit further, and reveal a cosmos more strange and wonderful than we ever imagined. For more than 2 centuries, Isaac Newton was more than just a scientist. He was the king of physics. His ideas weren't just theories, they were considered absolute laws of nature, as solid and unchanging as a mountain. Imagine a universe where everything is predictable. If you know the position and speed of an object, you can know exactly where it will be in the future. This was the universe Newton gave us. His 3 laws of motion and his law of universal gravitation were the keys that unlocked the secrets of the cosmos. They explained why planets stay in orbit and why a ball thrown in the air follows a perfect arc. These ideas were so powerful and so effective that they became the foundation of our modern world. Engineers used Newton's laws to build bridges, design machines, and launch cannons with precision. Astronomers used them to predict the return of comets and even discover new planets they couldn't see, just by observing the gravitational pull on other worlds. Newton's physics worked. It worked so well that it became a core part of education everywhere. Students in schools all over the world learned his equations. It was the first thing you learned in physics, the starting point for understanding how the world works. The universe, according to Newton, was a neat and tidy place. Space was a fixed, unchanging stage. It was an absolute 3-dimensional grid. Time was a river, flowing at the same constant rate for everyone, everywhere. It didn't matter if you were sitting still or flying through space on a cannonball. Time ticked by at the same pace. This idea of absolute space and absolute time felt right. It matched our everyday experience. It was common sense. This made his theories even more powerful because they were not only mathematically elegant but also intuitively easy to grasp. Because of this incredible success, most scientists believed that physics was nearly complete. They thought that all the big discoveries had been made. The future of science, they believed, was just about filling in the small details and making measurements more and more precise. Newton's universe was thought to be the final description of reality. It was a beautiful, majestic clockwork, set in motion by a divine clockmaker, and running perfectly according to the laws its creator Isaac Newton had discovered. There seemed to be no reason to question this perfect picture. It was the ultimate truth. Just when we thought we had the universe all figured out, a young patent clerk in Switzerland started asking some very big questions. His name was Albert Einstein. He wasn't a famous professor in a grand university. He was a humble thinker who spent his days looking at inventions and his free time thinking about the cosmos. Einstein had a deep respect for Newton. He understood the power and beauty of Newton's laws, but he also saw that there were some strange new discoveries that didn't quite fit into Newton's neat and tidy universe. He was brave enough to challenge ideas that had been accepted as fact for hundreds of years. Einstein's genius was in his ability to perform thought experiments. He would imagine situations that you couldn't actually create in a lab. His most famous one started with a simple question: what would you see if you could ride alongside a beam of light? According to Newton's physics, you should be able to catch up to it. But another great theory, from the scientist James Clerk Maxwell, said that the speed of light is always the same, no matter how fast you are moving. This was a direct contradiction. How could the speed of light be constant for everyone? It didn't make sense in Newton's world of absolute space and time. This puzzle obsessed Einstein. He realized that for the speed of light to be constant for all observers, something else had to be flexible. Something we thought was absolute had to be able to change. What if that something was space and time itself? This was a radical, revolutionary idea. It went against 2 centuries of physics and against our everyday common sense. Einstein suggested that time could slow down and space could contract or shrink, depending on how fast you were moving. He was proposing that the stage of the universe wasn't fixed. It was a dynamic, stretchy fabric, so Einstein didn't set out to prove Newton wrong. He set out to solve a puzzle. He was trying to make 2 great sets of ideas, Newton's laws of motion and Maxwell's laws of light, work together. In doing so, he became the ultimate challenger to Newton's throne. He wasn't just fixing a small error, he was proposing a complete shift in our perception of reality. He was telling the world that the solid foundation of physics, built by the great Isaac Newton, had some deep cracks in it, and he was the one who was going to show us where they were and how to fix them. At the heart of the showdown between Newton and Einstein is one of the most familiar forces in the universe: gravity. For Newton, gravity was a mysterious force that acted at a distance. He imagined it as an invisible rope pulling 2 objects toward each other. The bigger the objects and the closer they were, the stronger the pull. This idea is called the law of universal gravitation. It explained why an apple falls to the earth and why the earth orbits the sun. It was a simple, powerful, and elegant explanation. Newton himself famously said he didn't know what gravity was, but he could describe how it behaved perfectly. His theory described a force that acted instantly across any distance. If the sun were to suddenly disappear, Newton's equations said that the Earth would instantly fly off its orbit and into the cold darkness of space. The information that the sun was gone would travel instantaneously. This idea of instant action at a distance always bothered some people, including Newton himself, but the math worked so well that everyone accepted it. For 200 years, this was our picture of gravity, an invisible, instantaneous pull that reached across the vast emptiness of space, keeping the cosmic dance in perfect rhythm. Einstein offered a completely different picture. In his view, gravity is not a force at all. He said that massive objects like the sun don't pull on other objects. Instead, they warp or bend the very fabric of the universe around them. He called this fabric space-time. Imagine placing a heavy bowling ball on a trampoline. The trampoline sheet sags and curves. Now, if you roll a small marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball. For Einstein, this is what gravity is. The Earth isn't being pulled by the sun, it's simply following the straightest possible path through the curved space-time created by the sun's mass. This new idea of gravity as curved space-time made a very different prediction. If the sun were to vanish, the news wouldn't travel instantly. The change in the fabric of space-time would travel outward like a ripple in a pond. These ripples are what we call gravitational waves, and they would travel at a specific speed, the speed of light. So, in Einstein's universe, we wouldn't know the sun was gone for about 8 minutes, the time it takes for light and gravity to travel from the sun to the Earth. This was a profound contradiction to Newton's view, changing gravity from an instantaneous force to a consequence of the geometry of the cosmos. For a long time, Newton's laws seemed perfect. They could predict the motion of planets with incredible accuracy. But as our tools for observing the universe got better, tiny little problems started to appear. These were the first cracks in Newton's magnificent structure. One of the most famous problems was the orbit of the planet Mercury. According to Newton's laws, Mercury's elliptical orbit around the Sun should be stable. However, astronomers noticed something strange. The orbit itself was slowly rotating or precessing over time. It was a very, very small effect, but it was real and it was measurable. Scientists tried to explain Mercury's wobbly orbit using Newton's physics. They thought maybe there was a hidden planet, which they even named Vulcan, tugging on Mercury and causing the strange behavior. They had used this trick before to discover Neptune, so they were confident. But they searched, and they never found Vulcan. The mystery remained. Newton's powerful law of gravity, which worked perfectly for all the other planets, failed to completely explain the orbit of the planet closest to the Sun. It was a small crack, but it hinted that something fundamental was missing from our understanding. Another crack appeared when physicists started studying things that move very, very fast, close to the speed of light. Newton's laws of motion assume that mass is constant. An object's mass is always the same, whether it's sitting still or moving. But experiments with tiny particles in the late 19th and early 20th centuries showed something different. As these particles were accelerated to incredible speeds, their mass seemed to increase. It became harder and harder to speed them up, as if they were getting heavier. This simply did not fit into Newton's framework, where mass was an absolute property of an object. These were not the only issues. Newton's idea of an absolute space and time also began to crumble under scrutiny. His framework suggested that if you were on a train and threw a ball forward, the speed of the ball relative to the ground would be the speed of the train plus the speed of your throw. This makes sense, but Maxwell's equations for light predicted that if you were on a super-fast spaceship and turned on a flashlight, the light would move away from you at the speed of light, not the speed of your ship plus the speed of light. This contradiction between motion and light was the biggest crack of all, a sign that a new theory was desperately needed. Albert Einstein looked at these cracks in Newton's universe and realized they weren't small problems that could be patched up. They were clues to a deeper reality. His first major correction came in 1905 with his theory of special relativity. This theory dealt with objects moving at constant speeds. To solve the puzzle of the constant speed of light, Einstein proposed his radical idea that space and time are not absolute. He showed that the faster you move through space, the slower you move through time. This effect is called time dilation. He also showed that objects contract in the direction of motion, an effect called length contraction. This theory elegantly explained why the mass of a particle seems to increase as it approaches the speed of light. Mass and energy, Einstein said, are two sides of the same coin. They are interchangeable. He captured this profound idea in the most famous equation in history, E equals mc squared. This equation means that energy equals mass times the speed of light squared. Because the speed of light is such a huge number, a tiny amount of mass can be converted into a tremendous amount of energy. This explained why it gets harder to accelerate particles to light speed. The energy you put in is being converted into more mass, not just more speed. But special relativity only dealt with constant motion. It didn't include acceleration or gravity. For 10 more years, Einstein wrestled with the problem of gravity. This led to his masterpiece, the theory of general relativity, published in 1915. This was his new theory of gravity. Instead of a force, gravity was the result of mass and energy warping spacetime. This theory of curved spacetime perfectly explained the mystery of Mercury's orbit. Mercury is the closest planet to the Sun, where the curvature of spacetime is strongest. Its wacky orbit was simply the planet following the warped geometry of space around our star. Einstein's math predicted the exact amount of wobble that astronomers had observed. Einstein's theory made other stunning predictions. It said that gravity could bend the path of light. In 1919, during a solar eclipse, an astronomer named Arthur Eddington led an expedition to take pictures of stars near the Sun. He found that the starlight was indeed bent as it passed by the Sun's massive gravity, by the exact amount Einstein had predicted. This was a triumphant moment. It was the first physical proof that Einstein's strange new universe was the real one. He hadn't just fixed Newton's math, he had replaced the very concept of gravity with a more profound and accurate idea, changing modern science forever. You might think that after rewriting the laws of the universe, Einstein would have been dismissive of Newton. You might expect him to see Newton's work as flawed and outdated. But the opposite was true. Albert Einstein had the deepest admiration and respect for Isaac Newton. He saw Newton not as a rival, but as a brilliant pioneer who took the first and most difficult steps. Einstein once wrote that Newton was the most luminous and profound intellect that has ever been given to the world. For Einstein, Newton's achievement was a unique and monumental moment in the history of human thought. Einstein understood how incredibly difficult Newton's task was. Before Newton, science was a jumble of disconnected ideas and superstitions. There was no single unified system to describe the physical world. Newton was the first person to create such a system. He developed the mathematical tools, calculus, that he needed to describe his ideas. He found a set of simple, universal laws that could explain both celestial and earthly motion. He connected the fall of an apple with the orbit of the moon. This was a breathtaking leap of creative imagination. Einstein recognized that this first great synthesis was the hardest step of all. In Einstein's view, his own work was a natural continuation of Newton's. He saw himself as someone who came along later, with the benefit of 2 more centuries of scientific discovery and mathematical development. He had more clues to work with, like the puzzle of Mercury's orbit and the constant speed of light. Einstein felt that he was simply making a necessary correction to a magnificent theory. He said that he stood on Newton's shoulders, a famous phrase Newton himself had used to describe his own debt to earlier thinkers. This humility is a hallmark of a true scientific mind. So, when Einstein called Newton the greatest genius, he was looking at the context. He was considering the intellectual darkness from which Newton emerged. Newton had to invent the very language of modern physics. Einstein, on the other hand, had Newton's language to work with and improve upon. He believed that the creative spark needed to build something from almost nothing was a greater feat than refining an existing structure, no matter how profound that refinement might be. It was an act of supreme generosity and intellectual honesty from one giant of science to another. If Einstein's theories are more complete and accurate, you might wonder why we still teach Newton's laws in every school and university. Why do we bother with an incomplete theory? The answer is simple: because Newton's laws are incredibly useful, and in most situations they are more than good enough. For the vast majority of things we experience in our everyday lives, Newton's physics works perfectly. His equations are much simpler to use than Einstein's complex tensor calculus. If you want to build a bridge, launch a satellite, or calculate the trajectory of a baseball, Newton is your guy. Think of it like a map. A map of your city is not a perfect representation of the Earth. It's flat, while the Earth is a sphere. But if you just want to find your way from your house to the library, the flat map is exactly what you need. It's simple, and it gets the job done. You don't need a giant, complicated globe that accounts for the curvature of the Earth. Newton's physics is like that flat map. It's a fantastic approximation of reality that works beautifully within its limits. It only starts to break down in extreme situations, for things that are very, very massive or moving very, very fast. For most engineers and scientists, the difference between Newton's predictions and Einstein's predictions is so tiny that it can be ignored. The correction that Einstein's theory provides for the orbit of the Earth, for example, is incredibly small. Using his complex equations would be overkill. Newton's laws provide a powerful foundation, a first step in understanding the physical world. You have to learn to walk before you can run. In the same way, students must learn the fundamentals of Newtonian mechanics before they can tackle the mind-bending concepts of relativity. It gives them the essential tools and intuition for thinking like a physicist. So Newton's theories are not wrong in the way we usually think of the word. They are incomplete. They are a special case of Einstein's more general theory. Einstein's equations, under conditions of low gravity and low speed, actually simplify to become Newton's equations. This shows that Newton's work is not discarded, but rather embraced within a larger, more comprehensive framework. His legacy is not diminished. It is the solid ground upon which the entire skyscraper of modern physics is built. We still stand on the shoulders of this giant every single day. The story of Newton and Einstein brings us to a final, fascinating question. What is the true nature of genius? Is it found in the person who creates the first grand system, the one who brings order out of chaos? Or is it found in the person who sees the subtle flaws in that system and dares to imagine a new, more complete reality? Is genius about original creation, or is it about profound correction? This is the heart of the debate. Newton was the ultimate creator. He built the very framework of classical science from scattered pieces, giving us our first coherent map of the universe. Newton's genius was in his synthesis. He took observations from the heavens and the earth and united them under a single set of mathematical laws. This had never been done before. It was a monumental act of intellectual creation that shaped human thought for centuries. He established the rules of the game. He gave us the language and the tools to talk about the physical world in a precise, logical way. This act of pure foundational creation is what led Einstein to place him on the highest pedestal. It's like composing the first symphony in a world that had only known simple folk tunes. Einstein's genius, on the other hand, was one of critical insight and revolutionary reimagining. He didn't start from scratch. He started with the beautiful symphony that Newton had composed and noticed a few notes that were slightly out of tune. But to fix those notes, he didn't just change a few chords. He had to invent a whole new kind of music theory. His genius was in recognizing that the very concepts of space and time, which everyone took for granted, were the things that needed to be changed. This was an act of incredible intellectual courage and profound correction. In the end, perhaps the question of who was the greatest is the wrong one to ask. Science is not a competition, it's a relay race, where each runner passes the baton of knowledge to the next. Newton was the runner who started the race, setting a blistering pace and defining the track itself. Einstein was the runner who took that baton and, seeing that the track needed to curve in ways no one expected, ran in a new direction, revealing a far grander stadium than anyone had ever dreamed of. Both were essential. Both were titans. Genius, it seems, comes in both forms: the power to create and the wisdom to correct.